Okay ji, welcome you to this new video lecture. Today we will discuss reduction of multiple subsystems. So actually normally we have some block diagram. So first of all we have block diagram, help of which we can represent our system. So now in block diagram, first type of connection we have the series form, or sometimes it's called as cascade form. So in this we have two blocks connected in cascade. So we can solve this by just multiplying these two blocks. So as there's input, this is your output. So now the next one is the parallel form. In parallel form, we normally have a single input going to different blocks. And then the output is combined. So output is sum up. This is input and this is output. So for this block we can represent by a single multiply by adding all the inputs. So adding all the blocks, so this will reduce it into a single block. And third one, feedback form. Now in feedback form is something like you have your input, you have a block here, another block in the feedback. So this is a feedback connection. So the result can be solved is equal to a single block. Just go from input to output and just look at how many blocks you have, and the transfer function of those blocks, just multiply them. So for example, from R to Y we have only one block, we wrote it on the top and then put 1, and look at the sign here. If it is minus, put plus here. If it is plus, then put minus here. Then what you do, go in the loop, and in loop you have two blocks, just multiply it. So this is the way you can reduce your feedback. So these are basic three blocks we can use. Normally we have, and we have solution. So after that, then we have some, for example, we can moving block. Blocks to create familiar forms, so that we can apply these basic three rules to solve those. For example, if you have an input, okay, R, and there's another input X that are plus minus, doesn't matter, and then there's a gain G and you get the output Y. So this can, if I want this to go in that direction, so this means that this this is r plus x times g, or we can write it rg plus xg. So it can be written as rg plus similarly xg. If it is minus plus, doesn't matter, and then output. So this is the same, because if I want to write the equation for this one, y is equal to g times r plus x. Here what is the equation look like rg plus xg. So we have same representation in both cases. Now there's another one where, for example, if a block is here with the r and we have a summation point, a junction is here, and this is x and this is our y. So if I want to move this block to further height, so it can be easily moved. But the thing is, if I move this block to here to make the consistency, because this is just x is adding here, so I need to divide here 1 by g with x, so that it will maintain the mathematical relation with the output. Now relation is same. Okay, so this way you can do manipulations. And there's another one, third one, where we have input block is there, we have another input, and so on. Now for example, this is the input. Now if I want to take this block back, so we can say that this is with g. Now it's okay for first one, but for second one, to make the relation consistent, I need to divide g here. Similarly for this block, the gain I need to divide here. Now these are consistent. Similarly the last one, easy one. So if you have a g and you have multiple points ahead, so you can rewrite it in this way. These two are equivalent block representations. So these are few block representations. Now we have a very limited that we can do with these type of block representations. Okay. Now let's do an example. Start with a very simple example, and we say that we have an input and we have again g1, then we have a feedback path here, then we have another feedback path, then we have another feedback path. Now we have g2 and g3. Then we have output. Then there's a first feedback with h1. Then there's a second feedback with h2. And then there's a third feedback with h3. Now to solve this, if we look at, so this becomes a series one, and then this whole becomes a feedback. When we solve this, we come up with a single block, then again this become a feedback, and then single block, and so on. So to reduce it, the idea is that because these are three are in parallel, we can add them as well, because this is plus and this is minus. So you can, because these are connected into a single bit, and this input and output is same, so we can rewrite it at g1, then a feedback, because these two are in cascade form, so we can write it at G1 G2, and these three are adding with same input, so we can write it a single block, and we can say that okay, if we make it a feedback one, then we say that we have H1 minus H2, so that this sign is consistent, and plus H3. Okay. Now this will make our life very easy, and just write the transfer function. This block is equivalent to this one. So if I go in this direction, so I have G1, G2, sorry, G2 and G3. This is G2 and this is G3. Now for feedback, so I have to come in the loop, and I say 1 plus in the loop we have G2, G3 time H1 minus H2 plus H3. So this is the solution we get by simplifying this block diagram. So there's another example that we look at, and then we move to next one. Example is that we have input, and then we have again G1, then another feedback term with another gain G2, but there's another branch coming into it. Okay. And this branch is also summing up here. The feedback term, that is H2. There's another feedback term, that is H1. After that we have another feedback coming to this one, and we have G3, then we have H3. So if you look at this look like a bit complex, because there are a lot of blocks that are involved in it. So we will try to solve it one by one. So now the first thing is we just want to pick this point from here and take it here, so that it can easily solvable. So if I do that, what happened, and this is also a feedback path, so I can solve this point and that one. So we have plus minus G1 as it is, this plus and this is minus, feedback term as it is, and we put G2 here. Okay. So what we did actually, we just plug this point and move here. We have same H2, and we have same H1 here. So now when we move this point to this, look here, this input is multiplied by G2, then add this one. So if we move this to here, so I need because this need to be divided, because there's no gain with this one. If I move to next after this block, so I need, in that case I need to divide it. So in that way this becomes 1 over G2. Now things are look good. Okay. Now after this is a very simple feedback one. We can solve it as G3 divided by 1 plus G3H3. Now we can reduce this one as well. So after that this is the feedback, then another feedback. So let me so this reduced to 1 plus 1 over G2, right? So this one reduced to G2 divided by 1 plus G2H2. Okay, so let's make it here. We have G1 times G2 1 plus G2H2, then the feedback with H1. Then we have 1 over G2 plus 1 times G3 divided by 1 plus G3H3. Now things are look quite simple, just cascade multiplication and feedback, then multiply, you get the result. So this is the way we can easily solve the block diagram. So these become if I wrote the overall one, so this becomes R. So we have G1 G2 all divided by 1 plus G2 H2 1 plus G1 G2 H1. Then we have another block. This block is 1 plus 1 over G2 times G3 whole divided by 1 plus G3H3. Then is the output. Now to solve this, so there is a single block with input R and output Y of S. So in this case this becomes G1 G2 times 1 plus G2 this becomes G3, it is cancelled out, so it becomes 1 plus G2 whole divided by 1 plus G2 H2 and plus G1 G2 H1. Then we have 1 plus G3 H3. So this is the solution we are getting when we reduce the block diagram. Now this is very easy doing it by applying the different algebraic relations and reduce the block diagram. The question is how we can solve some complex one. So in that case we study a new technique is known as signal flow graph. So signal flow graph actually help us to solve these problems easily. So in signal flow graphs we have two things. One is the branch and other is known as node. So you have a branch with a gain and you have a circle node. So this is branch, this is node. The node is represented by input or output. This is for input output and this is for branch is for gain. between input output. Now the idea is that so we can add the gains coming to a branch, and we can calculate the gain. For example, if we have point 1 with gain G1, then gain G2, okay, we say this is R and this is Y, so this is equivalent to G1 G2 Y, right? So we have to use a technique to solve these type of problems that represented by flow graph. So how we do that? So we use a formula is known as Mason's rule. So Mason rule tell us how to solve this type of graphs. Okay. For example, if this is a graph and we want to solve it, G1, so this is your input. Then we have another node represented by G2. Then that node is coming back with minus, so with H1. Then this go further with G3. Then we have another node, then G4, then we have another node, that is G5, then we have another node, that is G7, then we have another node. Okay, so this is my output. Now we have this from this node there is a feedback like this, with H2 is the gain of the branch. Similarly, there is a feedback from here to back here with H3. There's feed forward one that goes from this point to that point, and we call it as G6. So this is basically a graph, and we want to use to solve this graph. So before this graph, if I start from a single point and ends at the output, we call it forward path. Okay, so the path between input and output is known as forward path. Okay, so we have forward path, that's path between input to output. So for example, how many paths in this graph? Look here, if I start from R, I will traverse through G1, then G2, G3, G4, G5, G7 and output. This is one path. Second path, G1 to G2, G2 to G3, G3 to G4, and then G6, then G7, and reach the destination. So there's no repeating node in the forward path, no repeating node. Okay, so there are two forward paths. So in this example, we have forward path, that is G1, G2, G3, G4, G5 and G7. So this is again a first forward path. Second forward path is G1, G2, G3, G4, G6 and G7. So this is the second. These two are the gains of the forward path. Okay. Now the next thing is Loops means that if you start a point and you come back to that point after traversing is known as loop. For example, if I start here and go this node, then I come back to this node again where I start. So this means that this is a loop. So this is a closed path and this is a loop. Loop 1. Look here, there's another loop. Loop 2. Again there's another loop. We call it as loop 3. Again there's another loop. Now this loop is starting from here, going in this direction, coming back with another loop. So this is loop number 4. Okay, there's no other loop in the path. So there are 4 loops. Okay, so loops are those paths where you start and come back to the same node. Now after that, understanding this thing, so let's see the Mason's rule. What is Mason's rule? Mason's rule is very simple. It says that the transfer function you want to calculate, that is from output to input, actually equal to summation of tk lambda k divided by lambda. Now here k is number of forward paths. Now tk is the gain of kth forward path, and then we have delta is defined 1 minus sum of loop gains, then plus, because we have alternative sign, summation of non-touching loop gains taken two at a time. So first you have just a single loop gain, but here you have to write all those loops that are not touching and then take the gains of those non-touching loops. Now then we have minus sign, then summation. So non-touching loop again taking 3 at a time. At a time. Then plus, then you have continue this thing, then 4 and so on. Now delta k actually equal to delta minus sum of loop gains terms in delta that touch the kth forward path. Now this formula will be understand when we do the example and we try to solve that example. Now first of all we have to find the k in this formula. Now if I go back, so for this k, how many forward path? So there are two forward path. So for this one, k is 2, and I know I just go there and next page. Let me rewrite and try to solve this. Now let me rewrite so that we can easily understand and solve this problem. Now we have this feedback here with H1, then we have another feedback with H2, that would be this one, then we have another feedback from here, this one with H2, H3, and that's it. So this is the whole phenomenon. Now here k equal to 2 and T1, gain for first one is G1, G2, G3, G4, G5 and G7, and gain for T2 here is G1, G2, G3, G4 and G6 and G7. So first path is going directly from here, second path is going from here, then move like this. These are two forward paths. Okay. Now next thing is we have to find the loop. So we have loop 1 with gain G2 H1, then we have loop 2 with gain G2 H2, then we have loop 3 with gain G4, sorry, this is G4 H2, then we have G4 G5 H3, then we have loop number 4, that G4 G6 H3. So these are possible loops. So we have 4 loops here. Now first of all find this delta. Delta is equal to 1 minus the sum of gains of the single loop, that is G2 H1 plus G4 sum. You have to add the gains, G4 H2 plus G4 G5 H3 plus G4 G6 H3. So this is for single loop. Then put plus sign and then take the combination of non-touching loops. For example, here this loop is not touching with this loop is not touching with that, and so on. So how many loops we have? 1, 2 and 3 loops. Look here, there no point is touching with this loop with all these loops, so we have to multiply these two, so it becomes G2 H1 time G4 H2, because these two are non-touching. I just multiply, then I put plus sign here, then I multiply with this one, that is because these three are touching loops, so I have only combination first with that one, then with that one, and so on. So second one becomes G2 H1 G4 G5 H3, then put plus sign, then we have G2 H1 time last one is G4 G6 H3. Then combination of 3 non-touching loop in this case is 0, so we stop here. Now delta of k, that for delta of k actually is very simple. We have to consider delta 1 when we are considering this forward path, and we have to minus all those loops that are touching this path. As you know that for both paths all the loops are touching, so this becomes 1 minus 0. Similarly, lambda 2 becomes 1 minus 0. So apply the Mason formula, so we get the result that g of s is equal to g1, g2, g3, g4, g5 and sorry, let me rewrite it. Because the only difference in between these two is here is g6 and here is g5, so I call it g7 becomes g5 plus g6. This is on the top because two forward path. Then I have to multiply with lambda 1, lambda in both cases is 1, so and divided by lambda. So this is the solution we are getting, and it's very easy to calculate the transfer function. Now to make ourselves further familiar, let's do another example. Example is that there's a point and it's going in with g1, then we have g2, then we have g3 and g4, then we have g5, then we have output here, and then there's the feedback between g4, that is with h2, then there's a feedback with g2, that h1, then there's another feedback, come back to another node, and then there's a g7, then there's a feedback with h4, then there's a feedback. Now this is g8. Now question is, to solve this problem, first of all we have to find the number of forward paths, so we have to calculate k. So this is your input R, so I will go with different color. I will start here and go in this direction. This is my first path. Okay. Now if I want to move in some other directions, can I do that? Let me check it. I don't think so. Path is repeating, so k is 1 here. So if k is 1, so t of 1 is g1, g2, g3, g4 and g5. Now lambda is, we have to write 1 minus sum of loops, so before this we have to find the loop. Loop 1 is g2 h1, loop 2 is g4 h2, and then we have loop 3, that is g7 h4, then there's a loop 4, that is g2 g3 g4 g5, and this is missing g6, right? So g6, g7, g8. So there are 4 actually loops. So now we have 4 loops. We just plug in the values for loop 1, g2 h1, and plus G7H4 plus G4H2 plus G2 G3 G4 G5 G6 G7 G8. Now we have to consider lambda 1 minus, consider all those loops that are not touching this. So we don't have any loops, so in that case delta 1 is 1. So there's this loop that is not touching with this one. Okay, so I have to put this one, only this loop, that is G7H4. Now apply the formula. Formula is G of S. Let me change the color. G of S equal to T1 lambda 1 divided by lambda. Now T1 is G1, G2, G3, G4, G5 times 1 minus G7 H4 whole divided by 1 minus G2 H1 minus G7 H4 minus G4 H2 minus G2 G3 G4 G5 G6 G7 and G8. So this is the solution we are getting for this problem. So the main idea is that we have to solve this using Mason rule that will help us to simplify the relation. Now the question is, we have a block diagram, how we can solve the block diagram using the flow graph. So this is the basic idea, because this will help us to make the solution easier. Now the main idea is we have to reduce the block diagram. The question is how we can reduce the block diagrams, or how we can solve the block diagrams using signal flow graph. So let me do it for you. For example, if we have a block diagram, so we can represent this. This is a block diagram. So block diagram is now we have this block diagram just to give you a understanding how we can represent this. So we have a quite complex diagram, so we didn't use this solution. Instead we will try to solve it with the flow graph. So this is the output, and we have a feedback here, that is G4. There's another feedback with H of S. There's another one that is going as a feed forward, that is with G3. So we ask you to solve this problem. Now the first thing is to convert this into signal flow graph. So how we do that? So the main here is this is the branch. This is a branch become nodes, and these nodes becomes branches. So the main idea is to convert branches to node and node to branch. Now let me block diagram to signal flow graph. So basic idea is convert nodes into branches and branches into nodes. So For that case, assume that this is a node, call it as RFS because this is a branch. After that, we have another node. Okay, so this is the node here, this one. Okay, so for this one, if I go further, it becomes a G1, then there's another node, then we have G2, then there's another node, then we have what you say 1 with the output Y. Okay, now there's also 1 because if there's no gain, then there's 1. So from this node to last node we have 1 is adding, so we can say that this is going to this one with a gain of G3. Now again, from the last node we are going back before G2 with a feedback of G4 with negative sign because this is minus. Again, from the last node to the first one we are coming in this direction with a minus H sign. So this makes things very easy for us. Just the main idea is to convert branches into nodes and nodes into branches. Now if we solve this problem, try to find the transfer function between Y and R. So it's very easy. First of all, we have to find the feed forward path. So we start from here and we will move like this. This is path 1. Now we start from here and move directly. This is path number 2. And if we start from here, okay, there's only 2 paths. So first thing we find is k equal to 2. Second thing is T1 is G3 and T2 is G1 and G2. Now third is loops. So first loop is this one. If I start from here, come back, so this is first loop, this is my second loop, this is my third loop. So there are 3 loops. So just write the equations for first loop is minus G2 G4, second loop is G1 G2 and H with minus sign. Then third loop is and minus G3 H, and fourth loop is fourth one become G1 G2 then H, no, only 3 loops. Okay, so this is the first one, this is the second one, this is the third one. So only 3 loops. After that we find it. Now the next thing we have to find the delta. So delta is 1 minus non-touching loops. It becomes minus minus becomes plus, so we have G2 G4 plus G1 G2 H plus G3 H, then minus non-touching loop. So is there any non-touching loop? I don't think so. 0, this is delta. Now delta 1 is also, there is no delta 1 because all the nodes are touching, so easily you can calculate the transfer function. So this is signal flow graph that help us to reduce the block diagram. I will stop here. We will continue further in next video. Thank you.